Did the AI community just pass the AGI threshold without realizing it? That's the question this new research paper aims to address. Titled "The Surprising Effectiveness of Test-Time Training for Abstract Reasoning," this research, coming out of MIT, explores one of the toughest benchmarks in AI. Many are familiar with benchmarks like GSM-8K and GPQ, but there's another notable one developed by Francois Challet, a senior staff engineer at Google best known for creating the Keras deep learning library in 2015. This specific benchmark, the RT, Abstraction and Reasoning Corpus, provides a unique challenge. Challet designed the RT benchmark to act as an IQ test for machine intelligence. What makes it different from other benchmarks is that it's resistant to memorization. While large language models, LLMs, operate like vast interpolative memories, ARC requires minimal knowledge beyond what's termed core knowledge. Basics like elementary physics, object perception, and counting, the sort of knowledge that a 4- or 5-year-old possesses. Each RT puzzle is novel and generally something that wouldn't appear online. Consequently, LLMs struggle with RT as they can't rely on previously memorized data. Challet notes that models typically performing well on traditional benchmarks fall short on RT. This MIT research paper on test-time training examines how LLMs, while performing well on in-distribution tasks, often falter on novel, complex reasoning tasks. In RT tests, LLMs struggle with out-of-distribution challenges, those unlike anything in their training data. This limitation underscores a key barrier to AGI, which demands systems capable of performing well on unfamiliar tasks across diverse scenarios. The researchers used test-time training, a method that involves updating model parameters temporarily during inference, using lost data from the input. This approach led to significant improvements in model performance on ARC, even surpassing human-level reasoning. These advancements are particularly noteworthy as RC has historically been considered a benchmark that LLMs consistently fail. Here's a simplified example of the RT task. The input shows objects with holes, where each hole is filled with yellow. LLMs struggle with these tasks because they haven't encountered similar examples before. This inability to solve novel tasks highlights the LLM's limitations with out-of-distribution reasoning. AGI, if achieved, would enable systems to tackle these kinds of unfamiliar problems, enhancing their reliability across industries. The study employed a variation of search algorithms, transforming input to make multiple predictions and aggregating these using hierarchical voting. This self-consistency approach, which selects the most frequently correct answer, enabled the model to perform closer to human levels. Remarkably, the model achieved a 61.9% accuracy, matching average human scores on RT, a first for an LLM on this benchmark. Some claim that this advancement means we're approaching AGI, akin to the frog in boiling water analogy. Incremental improvements in AI may be going unnoticed, yet they're leading us ever closer to AGI. While some argue that ARC is merely an abstract reasoning test, MIT's results reveal the potential of test-time compute and search algorithms for complex reasoning in AI. This idea of search-driven reasoning isn't new. A well-known example is AlphaGo's Move 37, an unconventional move that wasn't derived from prior human games but discovered through extensive search. True creativity in AI requires a system that can search through a vast range of possible solutions and find hidden gems that extend beyond traditional generalizations. The study suggests that as test-time compute increases, so does a model's ability to reason effectively. The MIT research showed a 6-fold improvement using only an 8 billion parameter model, underscoring the potential of this zero-first paradigm for advancing reasoning in LLMs. Some might recall Shane Lake from DeepMind discussing search-based improvements in past systems, like Hanabi, where a simple search algorithm dramatically boosted performance. As search methods evolve, we're likely moving towards AI systems capable of achieving advanced reasoning in out-of-distribution scenarios. The goal is to make AI search more sample-efficient, akin to human intuition, where world-class decisions are made with far fewer calculations than traditional AI. Even OpenAI's Sam Altman recently suggested that they now have a clearer path to AGI than ever before. If the Zero-First model achieves state-of-the-art performance by generating multiple answers during test time, we could see a new standard of reasoning in AI. The MIT studies methods suggest that combining different search tactics with optimization could accelerate us toward AGI, even as benchmarks saturate. What are your thoughts? Have we achieved AGI, at least in handling out-of-distribution reasoning? It's an exciting time for AI, and this research could signify a major step forward.